So, yeah, so today, Smriti, if you are there, you can start the recording, okay?
Yes, Professor, I've started.
Hi, sure, thanks. So, today we are going to see a little bit more about proteins. Yeah, yeah. So, proteins typically, they're so there's some sort of a traditionally there's some sort of a hierarchy about protein structures. Okay, the sequence of the amino acids, and we saw the amino acids last time, right? All the 20 canonical amino acids, and just the sequence of that is known as primary structure. Okay, here what you see that MGL blah 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 till FQG. Now this M, this is the N term, and this G is the C term. Okay, this is called as the primary structure. Now primary structure, so what happens is in the last class briefly we looked into uh, some of the secondary structures of protein, right? Those are alpha helices, beta sheets, and there is something called as loops. I've not discussed about loops, but in this class I'll show you a little bit about loops. Okay. So now because of the amino acid sequences, the sequence of amino acids, there is sometimes the formation of very local structures, right? And those local structures are typically known as secondary structures. And here, what you see in this, what is shown in the secondary structure cartoon, and these cylinders, there are all these cylinders. I think this is the structure of myoglobin, or could be hemoglobin also. They're very similar in structure anyway. So these cylinders are basically cartoon representations of alpha helices. Okay, we'll spend a little bit of time on the architecture of alpha helix in some time. So these are called as secondary structures. Now here in this protein, the beta sheets are not shown because this specific protein does not have any beta sheets or beta strands. Okay. And what you see in these gray wavy lines, these are nothing but loops. Okay. Now, what is the difference between the loops and the helices and the sheets? So, loops are such, for example, okay, hold on. So before let us complete it. So these secondary structures, now, these local structures are called as secondary structures, which could be alpha helices, beta sheets, and loops. Now, a coordination of all these things in a single polypeptide chain of a single domain protein, okay, is called as the tertiary structure. So here what you see is, so the primary sequence would be this, secondary structure would be these specific helices here, or it could be the loops, and tertiary structure is when all these guys are considered as a whole. That is the structure that the protein adopts, and it's called as the tertiary structure. Okay. Now there is something which is called as quaternary structure. Now quaternary structure is something which is even a higher order structure where several tertiary structures come together and form a large complex. Yeah. So here, for example, this is the structure of myoglobin. Here, okay, and this is myoglobin, and four such chains come together to form the quaternary structure. Now this is the case of hemoglobin. Now you can also take larger proteins. I think this is a RNA polymerase. Okay, in RNA polymerase, in the single colors define a single domain protein, and all these protein essentially they interact with each other and form a very large complex. Okay, yeah. So this would be the quaternary structure of a protein. Okay. And yeah, so this quaternary structure can be stabilized by the formation of disulfide bonds. They could be stabilized by the formation of non-covalent interactions. These are the mainly two interactions, either the disulfide bridges or non-covalent interaction, which stabilize the quaternary structures. Okay. All right. Now, before we go into these, I mean, let me spend a little bit of time on alpha helices. Do I have alpha helix here? No. Hold on. Let me tell you a little bit about alpha helices. Uh, yeah. So in the last class, can you still see my screen?
Yes, sir.
Great.
Yes, sir.
Yeah. So here, so in the last class, we quickly ran through these secondary structures. So alpha helices are very interesting because of the repetitive conformation or the local structure of these amino acids. Okay. So in alpha helices, now this termini is called as the N termini, and this termini obviously is the C termini, right? And as you go from the N termini to the C termini, you will see that the alpha helix is right-handed twisted. Okay, right? So that's what we see in nature. Most of the alpha helices, they are right-handed alpha helix. So and the reason is nothing but if you are to force them into a left-handed alpha helix, there are some steric clashes that happen because with the backbone atoms and the C beta of L amino acids, and that's why L amino acids, which are typically are the ones that you find in nature, they form the right-handed alpha helix and not left-handed alpha helix. Okay, and the other interesting feature about alpha helices is they are stabilized by the formation of I to I plus 4 hydrogen bond, right? These are the intramolecular hydrogen bonds. So for example, as we were discussing, so imagine this is the ith amino acid, yeah, and then this will be I plus 1, and the next one will be I plus 2, and the next one will be I plus 3, and this is the I plus 4th amino acid, and this I plus 4th amino acid NH, all the NHs are, you can see that they are essentially looking downwards, and all the COs are looking upwards. Okay, and they form these very stable hydrogen bonds. Okay, now the other thing about alpha helices is if you are to look into the single turn of a alpha helix, it's like a direct. So let's say that you are to go from this C alpha or a specific point onto this side to directly onto this side. Okay, this is called the pitch of a helix. Okay, single turn, or you can say from here to here. Okay, so directly if you translate, so if you hop from this point to this point, you will come across 3.6 amino acids. How many amino acids? 3.6 amino acids. And a 3.6 amino acid, and if you are to measure the distance of this 3.6 amino acid, it turns out that you have covered a distance of 5.4 angstrom. Okay, and now so now you know that 3.6 amino acids in alpha helix translates to 5.4 angstrom of distance. You can also calculate how much is the rise per turn, and this is a single turn, right? From this point to this point, this will be considered as a single turn. Okay, so if you calculate, which is nothing but divide your 5.4 by 3.6, it comes to roughly around 1.5 angstrom. So each amino acid rise is 1.5 angstrom in an alpha helix. Okay, these are the few statistics of an alpha helix. Please read about this in the textbook. The other thing is, there are alpha helices are very predominant in protein structure. Okay, and alpha helices which are the right-handed alpha helix, not the left-handed alpha helix. Okay, but it's not that left-handed alpha helices are not found in proteins; they are also found in proteins, but they are really rare. The reason, as I said, that these are steric reasons. Okay. The other interesting thing about alpha helices is, there are different types of helices also. For example, there is a helix called as a 310 helix. Okay. Now, what is a 310 helix? Imagine that if you hold this with a tweezer, this termini with a tweezer, and this termini with a tweezer, and pull it apart. Okay. You slightly pull it apart, then the helix becomes a little extended. Okay. Okay, and that extension leads to the formation of, meaning that what happens is, in doing so, you can make the helix elongated, meaning if there are 10 residues which encompasses probably maybe around approximately 3 turns. Okay, in that case the 10 residue will probably encompass 4 turns instead of a 3 turn. Okay, so that helix becomes a little elongated, and those helices are called as 310 helix. Now what does that term 310 mean? Okay, 310. Now if you are to consider a alpha helix, alpha helices will be called as something else. Let's take a look at what are these helices called as. So these helices, so let's count the number of hydrogen atoms which are present in a single turn in a alpha helix, okay, including the hydrogen bond donor, hydrogens, and etc. Okay, so let's count from here. So you have on oxygen 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so there are 13 atoms, okay, which encompass a single turn, including the hydrogen bond that is present in a alpha helix. And as I said, that in a single turn you have 3.6 residues. So technically alpha helix can be called as a 3.613 helix. Okay, likewise 310 helix is nothing but, so there are 3 residues as opposed to 3.6 residues in a 310 helix, and the hydrogen bond that stabilizes the single turn of a helix, there you will see 10 atoms as opposed to 13 atoms that you see in a alpha helix. Clear? Okay, please read about it. If you're a little confused, please read about it in textbooks. They're all written in the textbook. Yes, yes.
I think the 310 is actually tightly coiled, not
What?
elongated.
I mean, yeah, so that is a different term for a tightly what, coiled.
Yes, sir. If you want to have lesser atoms in one rotation, we need to have it more curved coil.
Yeah, so this is exactly what I'm saying, right? You pull this sides, so a spring, right? If you pull the spring, the same number of, imagine the spring is composed of atoms. Will that spring translate a longer distance with the same number of atoms, or will it encompass less distance?
It will take more with the same number of atoms. It will cover more distance.
Yeah, so that's what I'm saying. That's what happens in a 310 helix. Okay, right? But in
Sir,
that way,
sir,
what?
can you tell about the counting scheme again? Just briefly.
Once again, sorry.
Can you tell about the counting scheme
Yeah,
again?
sure. See, as you will see later today, that there are secondary structures which are called as loop. So alpha helix is one secondary structure, where interestingly what it turns out that the phi and the psi that we were talking about in the last class, the phi and the psi values of the subsequent amino acids in an alpha helix are very much close to a particular value. What is that value? We will discuss a little later. So it's sort of a repetitive structure, okay? Repetitive conformation that is adopted by the single amino acid. Terms are those where such repetitive conformation of amino acids are not present, but turns are something which are stabilized by a hydrogen bond. Now, alpha helix is also a repetition of a single turn. Okay. Now, this turn is stabilized by a hydrogen bond. For example, if you go from this C alpha, or let's say from this CO to this NH, so and where these are, this is the beginning of the helix, you will see this is the first hydrogen bond that you encounter. Okay, I mean between this, if you have meaning that if you just have amino acid till this, right? And you also have amino acids which are involved, or or the atoms which are involved in hydrogen bonds with this, but these amino acid will be coming later than that. Okay, so the shortest that you can form the hydrogen bond is between this oxygen and this NH. Okay, right? So that is why what people do is traditionally. So this is a single unit. So from here, from this oxygen to this NH, this is a single unit of a well, hypothetical unit of a alpha helix. And if repetition of these such units form a alpha helix. Okay. And I mean, I don't want to go into details. And this is something that is called as an alpha turn. You will not read about alpha turns now, not even in your entire studies in the UG. But yeah, so that's how this turn is stabilized. Okay. If we are to consider a single turn, if you are to consider, there is no alpha helix. Forget about these amino acids. Until this amino acid, not these amino acids onwards. Then you have only a single hydrogen bond that stabilizes this turn, and that hydrogen bond is between 13 atoms. Okay, so meaning that so if you count from this oxygen through the backbone until this hydrogen, which is forming the intramolecular hydrogen bond, will have 13 atoms, and that 13 atoms will encompass 3.6 amino acid residues, right? Because there are 3 amino acids all right in between. So this is one amino acid, right? And there is another amino acid, and there is another amino acid. But this part and this part belongs to the does not they are part of fragments of other amino acids. Okay, and they also contribute, and that's why it's called as 3.6 amino acids. Okay, so that's how the counting is organized. And same thing, alpha 310 helix. What I'm saying is, and if you pull it a little bit, then you will see that the hydrogen bond is formed between this NH and this CO. Now, if you count the number of atoms between this NH and this CO, so let's count. Okay, so you'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so instead of this NH here, you will have this NH, slightly translating sort of here, not here, but it will be a little different. Okay, and then hydrogen bond will be formed between this CO and that NH, and that will be called as a 310 turn, because in a single, if you translate 180 degrees or 360 degrees in the helix, you'll come across 3 amino acids. That's how helices are organized.
Okay, sir, understood.
Okay, good. So now you better read, okay? So that will clarify the other things. Okay, so this is a little bit about alpha helix and 310 helix. Now we will go back to our where we were. Hold on. Yeah. My mouse always behaves really weird. Yeah, here. Yeah. Okay. So, so as we were discussing in the last class or earlier classes, that the proteins are from primary sequence, primary structure. How do you go to actually this tertiary structures? From just a single polypeptide chain which doesn't have any structure. If you are to go to this such complicated structures that proteins adopt, there are forces that are involved, and those forces, like which we studied earlier, like there are hydrogen bonds, there are ionic interactions, there are hydrophobic interactions, simply put as van der Waals interaction. And it turns out that the van der Waals interaction are the ones which it's not that hydrogen bonds do not contribute to protein folding, but van der Waals interactions are the ones which have major contribution or the predominant contribution towards protein folding. Now, why is that so? So let's consider, so while going, because so I was also studying that, why there are lots of intramolecular hydrogen bonds, they stabilize the structure. Yes, correct. But what happens? So imagine, when a protein folds, and you have a single polypeptide chain. Forget about a protein. Let's say a single polypeptide chain which you have here. Hold on. Find, where's the pointer? Yeah. So you have this polypeptide chain in green. Okay. Now this polypeptide chain is present in water, right? And in water, what you have is you have the hydrogen bonds with water. You don't have intramolecular hydrogen bonds, but you have intermolecular hydrogen bonds. Now this is shown here. So the oxygen of the water engages in the formation of a hydrogen bond with the NH of the polypeptide chain, right? Now the CO of the amide backbone, it engages in the formation of a hydrogen bond with OH of the water molecules, right? Now, when the protein folds and it adopts a very nice secondary structure, this kind of structures are called as beta hairpins. Now, what happens is you have the formation of intramolecular hydrogen bonds, right? This is very similar to anti-parallel beta sheet that we have seen earlier. So this is sort of an anti-parallel beta sheet, okay? The only thing is that these two beta strands are essentially connected via a loop. Now, this kind of loops are called as beta currents, which we will see a little later. Now, the stability is certainly, there is certainly a contribution of the contribution of this intramolecular hydrogen bonds, but experimentally also you can show that these intramolecular hydrogen bonds are not the predominant things, that actually enforce the folding of this. So the same way, if this polypeptide, right, folds into a alpha helix, what will happen is, when it was unfolded in an unfolded state, the NHs and COs, well, it's shown that NHs and COs, you have seen that, there are many amino acids which are polar groups, right? Including aspartic acid, asparagine, tyrosine. You have the COs and the NHs, they engage in the formation of intermolecular hydrogen bond with water, right? Now, what happens is that in the unfolded state, they were engaged in formation of hydrogen bond with water. But in a folded state, in alpha helix, as we saw, that there is II plus 4 hydrogen bond forms. Right? If the polypeptide backbone, the CO was engaged in the formation of hydrogen, after it folds, it forms a hydrogen bond with the NH of its own backbone, right? So in terms of energy, there is not a large difference, that you can calculate. I mean, energetic difference that you can calculate if the hydrogen bond is either formed with water or intramolecular. Okay. So, but what happens is, so when proteins fold, these, in the, so here I don't know whether. Yeah, I don't have a nice figure, but I'm sure that you can see in the textbooks that, essentially what happens is when proteins fold. So initially, we can look into this structure itself. Initially, imagine there was a tyrosine residue here, there was a valine residue here, there was a tryptophan here. They are sort of well solvated, okay, or partially solvated, whatever, okay. They are not in proximity, but when they start to come in proximity, this is essentially what happens if you have a droplet of oil in water, right? You have a single droplet, and then what you do is you add another droplet. You can do this experiment, back at home, and stir a little bit, and these droplets will eventually come closer and stick to each other and form a large droplet. Standard micelles or whatever. Same thing, the same phenomenon that you have in proteins, right? Okay. Now, this is exactly what happens when proteins fold. So, see, these amino acids, where they were sort of solvated, the hydrophobic amino acids, to whatever extent they were solvated, they were not in proximity. But when the proteins start to adopt a folded structure, yeah, these amino acids come close to each other, and then the water molecules are sort of away from each other, okay? And then that leads to the folding of the protein. And that is why when you look into globular proteins, you will see that the interior of the protein, hardly there is the presence of any water molecule. It's also possible that in some cases there are water molecules that are sort of trapped in proteins, but this is rarely the case. So now one can argue that why did the protein start folding? Well, it's actually the other way around. So it's nothing but probably it's a random collision, And because of these random collisions, these amino acids essentially have to come closer, right? And when the amino acids have to come closer, the hydrophobic amino acids, they adopt such kind of structures. Okay. Now, such kind of structures is also, something that is guided by the steric interaction. Okay. Now, steric interactions are something that are very, very important in the folding of a polypeptide. Okay. Followed so far? So we will go to a little bit of different things now, more about steric interactions. But so far, if you have not followed, please ask any questions that you may have.
Sir, what is the difference between hydrophobic interactions and van der Waals forces?
Well, they're actually the same. What happens is, I may say that this hydrophobic interaction is one such type of a van der Waals interaction. Okay. Now, van der Waals interaction, there are many, many types of. See, van der Waals interaction are very, sort of very weak interactions. Okay. So, this hydrophobic interaction is a van der Waals interaction. There are many. So, for example, this pi-pi interaction you will study probably later in chemistry, or CH-pi interaction, or these are also van der Waals interactions. And these are, I think, the van der Waals interactions traditionally are classified by the energy associated with. These are very, very weak energies associated with. Okay? Follow?
Yes, sir.
Yeah, please read a little bit of chemistry. I'm sure that they will give you a much more quantitative picture about these hydrophobic interactions and van der Waals. But essentially, they come under the large umbrella of van der Waals interaction, weak interaction. Okay? But such, one must not ignore such weak interactions, because, you will remember, the example of a gecko. Such van der Waals interactions act in concert, meaning that there are many such interactions which forces the protein to adopt such structures. One such interaction is not enough. Many such interactions are required to form such folded states. Is there anything else? Then I can.
Good morning, sir.
Hi, yeah.
So actually, I had this one question. You mentioned that there is not much difference in strength between the intermolecular hydrogen bond that it has with water and the intramolecular hydrogen bond, right?
Yeah.
And that it ends up getting folded due to like a random collision that happens.
Yeah.
And so I had the question then, like, how does it maintain the folded structure then? Because like, won't the randomization also cause it to like get unfolded again?
Yeah, no, that's a very good question. See, essentially what happens is there is an energy difference, essentially, okay? So in terms of free energy, definitely your folded state is not, well, although you might be surprised to know that there is not a huge difference. Probably it's in the range of 5 to 10 kilocalories per mole. Okay, it's not a huge difference, the folded state and the unfolded state. So obviously you can imagine that the folded state is much more stable than the unfolded state. So what happens is, so once these guys come in proximity and the water is excluded, so it's some sort of an entropic effect. Okay, so sort of in the core there is so what happens is not just the entropic effect. What happens is, the core is stabilized by not only these hydrophobic interactions. Many amino acids, they engage in formation of salt bridges salt bridges. Okay, and because of the formation of these salt bridges, they stabilize. And what happens is, see, once the protein is folded, a hydrophobic core is formed, and in the hydrophobic core, the water is actually excluded. Now, if there was, if you do not form a hydrophobic core where the water is not excluded, then you may not have this the equilibrium shifting towards the folded state. Then it will be hovering forth and back and forth between the folded and the unfolded state. But once you form a hydrophobic core, right? Once you form a very nice hydrophobic core where the water is actually all of these, you can imagine the center of this protein. the water is excluded and thrown out. Now the waters cannot actually have access to the core of the protein. And since the water cannot have access to the core of the protein, the molecule cannot fold. Sorry, the molecule cannot unfold. Now to unfold it, what you have to do is you have to put some force. Now the force can come in terms of heat. Okay, the force can come in terms of very strong denaturing agents that can disrupt disrupt van der Waals interactions, hydrogen bonded interactions like urea and guanidinium hydrochloride. Okay, the force can also come from there are many ways. What people are doing nowadays, they use some sort of a tweezers, or they are called as optical tweezers, by which you can actually hold the N termini and the P termini of the folded and pull it apart. And by pulling it apart, you will see that the protein will unfold. And this is the hydrophobic core is the main reason. If you do not have the formation of a hydrophobic core, the proteins will not fold. Right?
Okay.
And
Yeah. Okay, sir. All right.
follow?
Yeah. Thank you, sir. Thank you so much.
Yeah, great. Okay, so I'll go to the next part then. Yeah. So we were seeing that the polypeptide chain. Now this is the polypeptide chain that you have, and as we discussed, the polypeptide chain itself, not the polypeptide chain, but the CO and the NH that we have, right? This moiety, the amide, is planar. Now the planarity comes from the delocalized lone pairs of electron that you have on the nitrogen onto the specific hybridized orbital of the carbonyl, and that's why you have a partial double bond character. Now this is something that you can also determine crystallographically. Okay. Now, so this bond is planar. Likewise, the next bond is planar, but these planes. So this plane and that plane, or this plane and that plane, they rotate with respect to each other because of the rotation between the C alpha C and the C alpha N. Now, as we said last time, that this rotation, the rotation between this plane and that plane, yeah, is called as a phi. This is a phi dihedral angle, and C alpha and C, this rotation, this torsion angle is called as the psi. Now, there is another torsion angle which is associated with the amide bond. Okay, we will see in a second. Hold on. Yeah, okay. So pictorially, how does it look like? So this is what it looks like. Okay. So these yellow balls, these are nothing but the C alphas. Okay. And so imagine this is the phi, and this is one amide bond, this is another amide bond, this is the next one, so on and so forth. And what you have is, no, sorry, these are not amide bonds. These are the C alpha C and the C alpha N. These are not the amide bonds. Okay. Okay. And what happens is, these guys can rotate with respect to each other. And, since these guys can rotate with respect to each other, they can form whatever structures you want them to form. Okay. The only thing is that, this is not exactly like a protein, how a protein would fold. Reason is because on these yellow balls, which are the C alphas, you have the C betas also, right? So if you have one C beta, let's say on this side you have a C beta, and you rotate this in such a way that the C beta which was on this, okay, it comes in proximity to this C beta, then that specific conformation will not be tolerated, right? Likewise, there are many such interactions. Or it's a very simple way of depicting, what happens, when different planes rotate with respect to each other. So we are going to, explicitly look at, what happens, when the specific planes in amide bonds rotate. Okay, so yeah, so I mean, this is nothing but this is just to show that what is a conformation and what is a configuration. I mean, you all know about it. For example, this 1 and 2, this is nothing but a conformation which is done by simple rotation of 1 and 2 bond. But but you cannot derive 3 by simple rotation of the amide bond here, right? This is something which is configuration. Okay, so now in proteins, we are talking about conformation. Now, since for example, if you have a polypeptide chain, it can adopt a alpha helical structure, it can adopt a beta sheet structure, it can adopt a loop structure. These are all conformations because here the same polypeptide chain, without inducing any bond breakage, you can change one conformation to the other conformation simply by rotation of the CC bonds, CC or CN bonds. Okay. Now, yeah, this is the L form, D form. We don't have to discuss this. Okay. Here, this is something that is interesting for you to know. Now, these are the statistics in a bond angle, bond distance statistics in a typical in an amide bond. Now, in an amide bond, what you see in this green is the amide plane. This is planar, right? And you can see that the C alpha C, this is around 1.51 angstrom. Any idea what is the bond length in ethane? CC bond length?
1.54.
Correct. Yeah, this is 1.54. Now you can imagine that this is certainly not a this is a sp2 hybridized. So that is why you don't have a 1.54 angstrom. This is slightly reduced. Okay. Now look at this angle. This is a C, so forget about the alpha, beta, whatever. So this is a CN bond, and this is also a CN bond, right? Both the bonds are connected to this nitrogen. One bond is 1.33 angstrom in length. Now, these distances have been determined by X-ray crystallography, where you can accurately measure the bond angles, bond lengths. Okay, so here this is 1.33 angstrom. This is an average across probably hundreds and thousands of molecules, and this is around 1.46. Any idea why is this so? Although both are C alpha N and CN, I mean not C alpha N, CN bonds.
Because there is resonance over here, like the
There is
a partial double bond.
Yes, same thing. Resonance, partial double bond, the same thing. Yeah, good. Yeah, see, this is actually the demonstration of there must be a partial double bond character in this CN, and that is why the bond length is shorter. You understand the rationale?
Yes, sir.
Yeah. So this is the direct demonstration of experimental demonstration of the feature that this is lower because you have a partial double bond character, but here you don't have a partial double bond character. Okay. And since you have a partial double bond character, it is difficult to rotate. There is an energy barrier associated with the rotation of this CN bond, but there is barrier is relatively less the rotation about this NC bond. Now, but does it mean that this CN does not rotate? That's not true. It does rotate. Okay. Right, yeah. So this is the depiction of the canonical forms. This is the keto form. The traditionally keto-enol tautomerism you would have studied. So this is like that. This is the neutral form. This is the charged form. And since you have the charged form, existence of the charged form, amides are actually acidic in nature. This is only because of the presence of this charged canonical form, right? In a proton, that hydrogen can happily adopt the positive charge, give it lone pair of electron. All right, that's why amides are slightly acidic in nature. Okay, now the other thing, yeah. So we were discussing about the phi and the psi, but there is another torsion angle which is called as the omega. Now, omega is the torsion angle which is associated with the rotation of the amide bond. I mean this CN. Okay. Now, as we said that there is a barrier. Certainly, yes, there is a barrier. But so in the barrier is essentially associated with because of the partial double bond. But remember this is a partial double bond, right? Right? We do not know the existence of the ratio of this. Maybe at a specific time, at time 0, this exists as a double bond character. Maybe at time 0 plus whatever seconds, this guy exists as a single bond. So there is still the possibility of a bond rotation. And since there is the possibility of bond rotation, this amide bond can exist in predominantly two conformers. Okay, one is called as a trans conformer. Okay, now the trans conformer is the one where the oxygen and the hydrogen are directly opposite to each other. Okay, so so you can have the torsion angle calculated. Torsion angle is the angle between two planes. You can take this. So this oxygen, carbon, nitrogen, and hydrogen. This will be 180 degrees. Now the omega, this is called as omega. Many people say that this can be calculated by the C alpha, C, and C also. Okay, irrespective of either you take the oxygen or the hydrogen or the C alphas, it's still the same. Okay, omega is 180 degrees. Now if you have a bond rotation where the NH and the COs come are sort of how do I call it? Will it be called as a collinear? Well, yeah, for the sake of simplicity, we'll say that omega equals to 0. They come in proximity to each other. That conformer, this is a conformer, okay? It's not a configuration, this is a conformation. This conformer is called as a cis conformer. Now, obviously, this is disfavored. The reason is very clear that you have the R groups, they come in proximity to each other, as opposed to here, where the oxygen and R is in proximity, but they are not exactly sort of a collinear kind of thing. Okay, there is a specific angle associated with this R and the O. You can also see it in the figure itself. Okay, but mainly the R and R. Imagine, this is a valine. Valine is something, where you have an isopropyl group. It's a large, bulky group here. And you have another valine. These two valines definitely would not prefer to come close to each other. Rather, they would prefer to stay apart from each other. Okay? All right. Now, so this is the trans, which is typically found in polypeptide cis. It's not that it's not found, but there are specific amino acids which actually favor the cis conformation over the trans conformation. Or let's say that many times it depends upon the. It also depends upon what are the amino acids that are present in the flanking sequence or so. Okay, but amino acids typically in polypeptide chain you will mostly come across the trans bond because of the energetically this is more favored than the cis conformation. Now there are amino acids which actually favor the cis conformation, or let's say that they have higher propensity to occur in a cis conformation than other amino acids, and that is proline. Okay. Now, can anyone suggest or speculate why proline prefers a cis conformation as opposed to meaning that proline can undergo cis transisomerism as opposed to other amino acids. Can anyone say why?
There is not much difference between the two energy of cis and trans because both have C alpha or C beta on both sides.
I don't understand this.
If you look at the figures, both are kind of similar, right, sir?
What are both kind of similar?
Below two figures, here C alpha has proximity C alpha, and in the other case, C alpha and C delta are in proximity.
Here you have the C alpha in proximity. Okay.
In the other case, we have C alpha, C delta in proximity.
Which C delta you are talking about?
In the below figure, it is given omega. I think it's C beta. I think.
So there will be collision between adjacent C alpha atoms in the cis.
There will be collision between the no. Hold on. I am not saying that why cis is more preferred, trans is more preferred. I am saying that why proline, being a special amino acid, has the tendency to show flip.
Because
is it because of its ring structure?
What does the ring structure do?
Sir, there is less double bond character in the C double bond O and N bond. CN bond.
There is less partial double bond character here.
Yeah,
Why?
because the lone pair of nitrogen will be uh, localized
Why?
because this ring form of this compound.
I didn't understand. You have to explain clearly.
If the proline has a ring, like
Right.
the ring is not planar one.
So what has that to do with the planarity of the ring?
So if the ring is not planar, then the both the bonds of the nitrogen, I mean nitrogen cannot be sp2 hybridized.
Nitrogen here cannot be sp2 hybridized. Why do you say so?
To maintain the non-planarity of the ring.
To maintain the non-planarity of
Secondary might, that's why.
the ring. But see, if the nitrogen becomes sp2 hybridized, right? You know, the ring can still be non-planar. Because you know, because so what you're doing is you're not altering the sp3 hybridized state of these carbons, right? And only because you're not altering the sp3 hybridized state of these carbons, you have this envelope kind of conformation, or this is so the ring couple will still be there.
So side chain is fused to backbone though.
So how does it help?
So the slide.
Let's say it reduces the energy difference between the cis entrons, I guess.
Sir, hydrogen bonding.
Hydrogen bonding.
So maybe
the side chains will not
Julian,
each other even.
so it is cyclic, and if the side chains were free to move, then there would be some conformations in the side chains as well, and so the side chains of both the central atoms under considerations can come closer to each other as much as they want, because they can rotate because the CC bonds in their side chains can also rotate. But in case of proline, as the bond is as the side chain is connected to the N itself, as Sanin pointed out, the side chains have less freedom to move.
What about glycine? Glycine is an amino acid. There are only 2 hydrogens. Would glycine prefer to form a cis peptide bond? If it's the steric reason, then glycine happily should form a cis peptide bond. No, there is no steric reasons. Steric influence.
Sir, is it related to the amino acid nature of proline?
It is related to the amino acid nature of proline. Yes.
So that it can work well in turns.
Sorry?
So that proline can do this, so that it can make very compact turns.
But you are not giving the rationale. It can form, but why? What is the reason?
Sir, because the carboxylic group on the proline carbon that cannot twist in order to be away from the O minus. So there will be repulsion in this case.
Sir, is it because those cyclic rings have to be out of the cyclic form of the C alpha helix on the external part of the
We are not
helix?
talking about alpha helix here. We are not talking about alpha helix here. There's nothing to do with alpha helix.
So there's no rotation allowed along one of the CN bonds. So I think that's why.
There is no rotation allowed about one CN bond.
Yes, sir. So like one of the backbones, like the nitrogen and carbon are connected through the cyclic chain.
Yeah.
Since one of them is constrained, I think that could be that is what is causing it to flip easily.
I'm not sure whether I really understand what you're saying.
So I'm not.
This, by the way, hold on. I'm looking at this picture now carefully. Uh, uh, I think this is drawn wrongly. Both are actually cis peptide bonds. Isn't it?
Yes, I think
One
the
is
diagram shows
highlighted.
that in the same polypeptide, we can have two proline molecules which show cis as and trans different
Yeah, yeah, sure. Anyway, please read about it, okay? We can discuss it in the next class. I'll just finish a couple of things. Okay. Yeah, so as we were discussing that, these are planar. The peptide bonds itself are planar, but what rotates typically are the phi and the psi. Now this phi is this C alpha N torsion, right? And the psi is that this CO torsion. Okay. Okay. Now what it turns out that some of these torsion angles, I mean all values of phi and psi in a polypeptide, even in a single dipeptide. Dipeptide is one, well, it's a little misnomer because dipeptide. You would think that dipeptide means two peptide bonds. That's not true. Dipeptide means two amino acids form a dipeptide. Okay. Okay. So in a dipeptide, meaning you have an alanine, which are involved in amide bond formation. Okay. So even in that, you cannot have all the values of phi and psi. I mean, all the rotations of phi and psi possible. Okay. The reason is shown here. So imagine, so in this case, here we are looking at a tripeptide, okay, meaning that you have two amide bonds. So one, for example, well, this is our well, no, this is actually a tetrapeptide. Okay, doesn't matter. Yeah. So what you no, even more actually, it's not even a tetrapeptide. So yeah. So this is the N term. Okay. So you have a histidine here, histidine followed by a tyrosine, okay, followed by a alanine, followed by this guy is a serine, and so on and so forth. Okay. But what we are doing is we are particularly focused in the uh, well here in a tripeptide, the torsion between two amide bonds, and that is between, for example, the histidine and the tyrosine, and the tyrosine and the alanine. Okay. Now this angle, say for example here, this is phi equals to 0 and psi equals to 180 degrees. Now what is phi equals to 0? Right? So phi equals to 0 is the one where we discussed that this is the torsion angle between this C alpha and the nitrogen, right? Now here what happens if phi equals to 0, meaning that this oxygen of the amide bond and this oxygen of the amide bond, right? So they are in very close proximity. And since they're in very close proximity, there is a lot of collision between them. That is why energetically such conformations where phi equals to 0 is not allowed. Whereas if psi equals to 180 is not a problem. Psi equals to 180 is, psi is the angle between this, right? This C alpha and this C, where this nitrogen, this C alpha, CO, C, carbon and carbon, alpha carbon and the nitrogen, they are exactly opposite to each other. You can see this, right? Imagine this as a Newman projection through, if you look through this CC bond and imagining it as a Newman projection, you will see that this nitrogen are above and below, right? And likewise, if you imagine a Newman projection through this nitrogen and this C alpha, you will see that these two guys, this this oxygen and this oxygen are actually facing each other. Okay? Or in a sense, you will see that this guy, this alpha carbon and this alpha carbon are facing each other, and consequently this oxygen and this oxygen will be facing each other. So this is a very high energy conformation which is not favored. However, if you rotate it slightly, yeah, so let's say, so yeah, so here we were discussing about this one, right? So you have phi equals to 0 and psi equals to 180 degrees. Now what happens if you rotate the phi? Okay, so if you rotate the phi to minus 180 degree, meaning that what you're doing is you are going in an anti-clockwise direction. In that case, it's a little difficult to see. Well, it's a little difficult to see for you guys, but okay, can you actually see that what has happened? See this, I mean, it's drawn in a different way, but what you could see is this carbonyl carbon of the histidine is here now, okay, right? And this carbonyl oxygen, the carbonyl carbon is here, the oxygen is here. That means, initially these two oxygens were close to each other. Now there is a large distance between these two oxygens, okay? So that is why even keeping the psi constant, if you have a phi of minus 100 degrees, this is tolerated. Likewise, if you rotate in a clockwise direction, what happens is, so now what happens, your yeah, this is a little easy to see because you can see both the carbonyl carbon. Here this is constant, right? So you're you're rotating this guy in a clockwise direction, this guy goes in the back side. So this carbonyl oxygen or the carbonyl group, instead of having here, now it has gone in a some sort of a 65 degrees angle, and this is what is depicted by this dark green, and this is tolerated, no problem. Okay. Now if you further rotate, keeping the psi constant, if you further rotate where your carbonyl oxygen goes to 135 degrees, depicted by this dark green circle, what happens is the carbonyl oxygen does not engage in a clash. Instead, the C beta of the tyrosine, right? It doesn't have to be tyrosine. It can be anything. It can be any amino acid because all amino acids except glycine have C beta, right? That C beta engages in a collision with the carbonyl oxygen. And that is why this phi 135 and psi degrees for any amino acid which is non-glycine is not tolerated. So that is exactly how the conformations of the polypeptides are essentially adopted. Some torsion angles are acceptable and some torsion angles are not acceptable. Okay. Now this is something that was done long time back by a guy called as G. N. Ramachandran, and he came up with a beautiful plot which is called as Ramachandran plot that actually shows, for a single alanine dipeptide, which is representative, you can imagine that would be representative of any amino acid except glycine. How would the plot look like, right? So this plot essentially this, right? So in your x-axis you have the phi minus 180 degrees to 180 degrees. Well, this is the same, right? It's some sort of a circular plot, right? Plus 180 minus 180 essentially is the same. Likewise, in the y-axis you have the psi, right? And it turns out all the regions in white are angles which are not allowed for a single dipeptide with alanine. Okay, whereas there are certain regions which are actually allowed, and those regions are depicted here. So this green region, this red region, and this gray region, okay, these are the regions which are actually allowed, and those regions later, it turns out that the conformations adopted by these by this dipeptide at this region can be named as certain specific conformations. Okay, and amino acids or amino acid residues which adopt conformations that will be predominantly in this region is called as alpha helix. Now that's what we were saying, right? In alpha helix, all the amino acids that are in the alpha helix have dihedral angle of minus 60, minus 40. Okay. In alpha helix, the the phi angles is average is minus 60 degrees, and the phi dihedral angle is average is minus 40 degrees. And in the beta sheet, okay, in this region, is dominated by, conformations which are adopted by beta sheets, and here the average conformation is minus 120 degree plus 120 degree. Okay. Interestingly, you can see that this guy is nothing but a mirror image of this. Now here, all your right-handed alpha helices, essentially come, meaning that the torsion angle. All the left-handed alpha helices torsion angles come here. Okay. Now this is a theoretical plot. Now many people what have done is they have taken the actual conformations of polypeptides in proteins, or the peptide bonds in proteins, and it turns out that yes, it is true that the proteins do have occupied these regions, predominantly these regions. You can see that this is a real plot from a protein. In this region you find, in this region you find, these are small clusters, right? And but it's not that they don't occupy or they do not have dihedral angles which are in this white space. Yes, there are occurrence of uh, such dihedral angles in this free space. Now one must appreciate that this was done theoretically on a model peptide. Okay, in those days, in 1960s when they did it, so there were no protein structures, no PDB structures, nothing. This was done based on purely hard sphere kind of calculations, and that is how they realized that this is how protein conformations would look like. And it's remarkable, one, the protein structures were really solved, and and their conformations were actually projected on a Ramachandran map. It still holds true. Protein, the polypeptides of the amino acids do adopt conformations which typically fall in these three different regions. Although nevertheless, there are sparsely populated conformations in the other regions as well. Okay. Now this is a plot. You can see that this plot looks a little bit different from this plot. If I'm not wrong, this is probably a glycine plot. Okay. Now so as I was discussing here, now see, this would be true, this collision, this high energy would be true for even for a glycine, right? But however, this conformation where you have the C beta, C oxygen, or if you have some conformations where the C beta of both the polypeptides, meaning that this guy and this guy clash, right? That conformation will not be acceptable for amino acids which are C beta, which are all 19 amino acids, except for glycine, because glycine does not have a C beta. Now proline will also be very interesting. Now you can now think about what sort of plot would proline have. Okay. All right. Now yeah. So how are we doing with the time? Are we over with the time?
Sir, it is 12:16.
Sorry.
Yes, sir. It's 12.
Okay. Yeah. So just a few more things. This is essentially nothing but depiction of certain conformers projected onto the Ramachandran plot. Just look at it, you understand. Now, yeah. So what I was saying that, so remember when the protein structure, I was showing you a hairpin. Now this is nothing but a hairpin where you have one strand, that binds with another strand in an anti-parallel manner, right? And both the strands are connected by two amino acids, and this turn is called as a loop. Okay, such loops are also predominant in proteins, and it turns out that these loops have very important role in protein folding, because see, this is the N terminus of the protein and this would be the C terminus. Now you see that this polypeptide, if it was not for this loop, this polypeptide will be straight. But it's only because of, let's say, the torsion angles, the phi side angles of these two amino acids, this polypeptide chain actually folds back on itself. Okay, that is why loops are very, very important in protein folding. Okay, and such loops are called as beta terms. Okay, now for example, in here, what you can see is, so this is a type 1 prime beta turn. Okay, and in type 1 prime beta turn, you have the hydrogen bond, and if you count the number of atoms involved in the turn, you will see that the following: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? If you recall, we said that in 310 helix, you also have 10, right? And it's very interesting. Well, I just thought I'll mention it. If you have multiple type 1 turns connected to each other, so this is one turn. If the next residues also adopt a beta 1 turn and the next residues also adopt a beta 1 turn, you will have nothing but a 310 helix. Okay. Likewise, you also have type 2 beta turns, which look a little different and they have certain different torsion angles. And in terms of protein structure, it turns out that these turns are something which are typically solvent exposed. Okay, these guys occur in solvent exposed regions, right? It's not very difficult to imagine. When you look at protein structures, you will see that, for example, here, or maybe here, you see, here these are the loops. They're not exactly beta turns. These loops, for example, let's say the polypeptide chain was going from here, here. Suddenly you have the loop and the polypeptide chain goes in a reverse direction. Okay. Also here in the back side, you see, those kind of structures are called as helix hairpins. So, the helix was going from here. Suddenly, instead of going straight, there's a loop and the helix goes in a reverse direction. And by such interesting loops, because of the formation of these loops, the proteins can actually adopt the formation of a very nice hydrophobic core and can fold, right? Yeah. So, okay. So, this graph, this heat map shows something which is also very interesting, is the propensity of amino acids to be present in an alpha helix. Okay, it's known that not all amino acids are predominantly found in alpha helix. It turns out that there are certain amino acids like alanine, you have beta branch, or they may have gamma branch, but these amino acids are very much favored in a helix. But amino acids like glycine, valine, threonine, okay, they are not very much favored in a helix. Likewise, proline also not very much favored in a helix. Okay, this is called as amino acid propensity of helices. All right. So with this, we will end protein. There are n number of other things to talk about proteins, but sorry, I think on 23rd you guys have you start your exams, don't you?
Yes, sir.
Yeah, I think we are done with the class. So Sarah, you can stop the recording. So if you guys have any questions, you can start just before. So 23rd onwards, you have your exams.